Welcome to the lecture for section 3.8, Inverse and Radical Functions. By the end of the lesson, you will be expected to be able to find the inverse of polynomial functions and restrict the domain to find the inverse of a polynomial function. First, let's recall what it means to verify two functions are inverses of one another. We have two functions f and g, and we say they are inverses of one another if for all x in the domain of f and g, we have f of g of x equals x, and g combined or composed with f of x is also equal to x. Let's start with example 1. Verifying inverse functions. Verify that f of x equals x plus 5 divided by 3 and f inverse of x equals 3x minus 5 are inverses. So we write f of f inverse of x equals f inverse of x plus 5 over 3 equals 3x minus 5 plus 5 over 3. All I did here was replace this with this because here I have that they are the same thing. They are equal to one another, so I replaced. The parenthesis here is unnecessary. It's more of a visual aid to help you see that this was lifted and removed and replaced with 3x minus 5. So I have 3x minus 5 plus 5 divided by 3, or 3x divided by 3, which is just x. So these two are indeed inverses. Independently, you can and should verify that this also holds. Let's look at example 2. Example 2, finding the inverse of a cubic function. Find the inverse of g of x equals x cubed plus 4. Graph both g of x and g of x inverse. So let's rewrite this. We know that g of x can be written as y, so this is y equals x cubed plus 4. To find an inverse, switch x and y. So we have x equals y cubed plus 4. Now we're going to solve for y. We can subtract 4 from both sides. And we have x minus 4 equals y cubed. Then taking the cube root of both sides leaves us with the cube root of x minus 4 equals y. So g inverse of x equals the cube root of x minus 4. Let's graph both of these on the axes provided. So bear with me while I change the zoom of these notes so that the entire, or at least more of this grid, becomes visible. All right, here's the grid. Go ahead and draw your x and y axes and label your points. All right, as you can see here, my grid is complete. So let's start by sketching our g of x. We have a cubic function, and it is just a translation of one of the toolkit functions from your book. If you notice, it's a graph of it. It is the graph of x cubed, which kind of follows this path up one way and down the other way for a little swirl or light curve. And it's moved up 4 places. So our graph is going to look something like this. And if you're wondering how I got those points, take a moment and make yourself a table and see if you can find these points. This one here is 1, 5. This one here is 0, 4. This is negative 1, 3. And then to find the x-intercept, recall, let g of x equals 0. So we have 0 equals x cubed plus 4. Negative 4 equals x cubed, where x equals the cube root of negative 4. And on your calculator, that's approximately negative 1.59. So this here is negative 1.59. Negative 1.59 comma 0. Now the easiest way to sketch our inverse is to start with the graph of y equals x. So this is this symmetric line here. And reflect this graph about this line. So that means we would swap our x and y points. Again, if you remember, the domain of the inverse is the range of the original function. So these are in the range of my original function, and so be in my domain of my inverse. So for my inverse function, I have the point 0, negative 1.59. I also have the point 3, negative 1. From this point, I know I have 4, 0. And then this tells me that my inverse graph should include the point 5, 1. And then we can just connect our dots. Remembering that these are going to be symmetric graphs. With that, turn to the top of the next page of section 3.8. Restricting the domain to find the inverse of a polynomial function. A function must be 1-to-1 before we can find its inverse. When a function lacks this property, we first restrict its domain. So this question asks us to find the inverse of h of x equals x minus 3 squared on 2 different intervals, so 2 different domains. And let's see what happens on each. So I'm going to start by writing this as y equals x minus 3 squared, then swapping my x and y to get x equals y minus 3 squared. Now I can solve for y. So I have the square root of x, and this is plus minus the square root of x, equals y minus 3. Adding 3 to both sides gives us 3 plus minus the square root of x equals y. So let's draw 2 graphs. So there are my 2 graphs. If you need to, take a moment and pause the video and catch up with the 2 sketches. So let's sketch h of x on both of these, emphasizing the restricted domain. So the graph of h of x is a parabola that is shifted to the right by 3 places. So I know my vertex will be here. I know I will have these symmetric points on either side of my parabola. And on the domain x is greater than or equal to 3, this is the part. This part on the right is defined, and this part is not going to be defined on this domain. So I'm writing it in as a dashed line. So again, this is our domain. Is x is greater than or equal to 3. Let's do the same, emphasizing our domain of x less than or equal to 3. Of course, if at any point you think I'm going too quickly and you don't see how I got these points here, you should pause the video and sketch out a table of values on some scratch paper and test these points out for yourself. So now in this domain, this portion here is defined and this portion is not. Now what does this do to our inverse graph? Let's start by identifying some key points. Our vertex is at 3, 0. Here we have 4, 1. Here we have, what is that, 5, 4. And let's go ahead and sketch our graph of y equals x. Let's go ahead and sketch our graph of y equals x as best we can. All right, as you can see, I now have the graph of y equals x sketched in both cases. Let's go ahead and reflect all of these points that we found. So this here, first of all, becomes 0, 3. This one here becomes 1, 4. That's this point becomes 1, 4. This point here becomes 4, 5. And that would make our inverse function look like this. So this is h inverse of x. That means on this domain, h inverse of x is the positive case. That is 3 plus the square root of x. And then of course here is our g of x, here is our h of x on the restricted domain. Now the points here are similar. We have 3, 0, we have 2, 1, and we also have 1, 4. Let's reflect all of these points about this line. So now we have 0, 3. This one gives us the point 1, 2. And this one here gives us the point 4, 1. And that would make our inverse look more like this. Actually, let me fix this really quick so I don't cut off what this point is. There we are. This is h inverse of x. Of course, this is h of x. So on this domain, our inverse becomes 3 minus the square root of x. Let's take a moment and see what happened. When we restricted it to the positive domain, we ended up with this inverse. When we restrict to our negative domain, that is less than or equal to 3, let's see what happened. Let's see what happened. When we restrict to the domain x is greater than or equal to 3, we end up with this inverse function. When we restrict to this domain, x is less than or equal to 3, we end up with this inverse function. In general, this is what we do. That is, we use the domain x greater than or equal to some value. So that would be this case here. So this is what you will do on your own when you're restricting domains. You will use this case. With that, let's look at example 3, part B. Part B restrict the domain of f of x equals x minus 4 quantity squared minus 3, then find its inverse. Write out the domain and range of f inverse in interval notation. So this is another parabola, another quadratic. We've already looked at these. When written in this form, we can identify the vertex here as 4, -3. That tells me we're going to want everything to the right of the x value of this vertex. So our domain is going to be x is greater than or equal to 4. Let's draw a quick sketch. So take a moment and draw an x and y axis that is clearly labeled. So here's my axis. If you do not have this sketched, take a moment, pause the video, and catch up with your sketch. Let's draw out f of x. Our original function, f of x, would be here. Our original function, f of x, has a vertex at 4, -3. That's down here. That also tells me that we're going to have the point 5, -2, and 6, 1. If you don't see this, please create a table, plug in these values for x, and see what outputs for y. Of course, we do have symmetric points on this side, so we should have another parabola side going this way. But since we've restricted our domain, I'm only going to sketch the one side. So our domain starts at 4 and goes to positive infinity. So this is our domain. Notice it includes the x value of our vertex and goes off towards the right, towards infinity. Remember, our inverse function will be symmetric about this line. So of course here we have f of x. So let's go ahead and find our inverse function. I'm going to start by rewriting f of x as x equals y minus 4 quantity squared minus 3. Let's add 3 to both sides to get y minus 4 squared on the right and x plus 3 on the left. When we take the square root now, we don't need to acknowledge the negative case since we've already restricted our domain. And finally, we can add 4 to get 4 plus the square root of x plus 3 equals y. So f inverse of x equals 4 plus the square root of x plus 3. And now let's go ahead and label these points and reflect them. This is the point 4, -3. This here's the point 5, -2. And here is 6, 1. And now reflecting these, we get -3, 4. We get -2, 5. And we get 1, 6. So our inverse function is going to look something like this. With that, turn to the top of the next page so we can look at example 4 and 5. Example 4, finding the inverse of a radical function. Find the inverse of g of x equals square root of x minus 5, then the domain of g of x. Use this to find the domain and range of g inverse. So this question is asking a little more than we usually get. Let's start by finding our inverse. So we want to rewrite this as x equals the square root of y minus 5. So I have x squared equals y minus 5, or x squared plus 5 equals y. So g inverse of x equals x squared plus 5. Now, what is the domain? Let's write some things down. We want domain and range of both g of x and g inverse of x. So let's start with our domain of g of x. What is the smallest possible value you could have inside of this radical? Well, we never want this radical to equal 0. So to find this domain, we solve y is greater than or equal to. We solve y minus 5 is greater than or equal to 0. This guarantees. So what do we never want inside this radical? A 0 is okay, but negative values are not okay. So in order to find our domain, let's solve the function. Let's solve the inequality. Let's solve the inequality y minus 5 is greater than or equal to 0. Adding 5 to both sides yields y is greater than or equal to 5. So this tells me my domain starts at positive 5 and goes out to infinity. I'm guaranteed that this will be the range of my inverse function. Now, what about the range of g inverse? Well, what is the smallest possible input we can have in our original function of g of x? What is the smallest possible input? Is 5 the smallest, or is some number larger than 5 the smallest? Clearly, our smallest possible input is 5. And if you notice, if we evaluate g of 5, we end up with the square root of 0 minus 5 equals, we end up with the square root of 5 minus 5 equals 0. So our range starts at 0. What happens as we get larger? Let's try evaluating, say g of 30. We end up with the square root of 30 minus 5 equals the square root of 25 equals 5. And we can keep going. I can put in 105 and we'll end up with 10. And we can just keep putting in larger and larger values and we'll get closer and closer to infinity. That tells me that this is the domain of my inverse function. So here is our inverse function, and here are the domain and the range for both. Let's look at the last example. Before we move on to the final example, let's verify that we got all of this correct using some online software. You should already be familiar with GeoGebra, so go ahead and take a moment and open it up on your own computer, either the online version or the software. If you notice, I prefer the software version, not the online version. So let's leave it here at graphing, and I'm going to give us some space so we can see our original function. And I'm going to change it to graphing mode and kind of get a window that I think works. So I'm going to start by graphing y equals the square root of x minus 5. And here is my graph. What is the domain of this? The smallest possible input is 5, and it goes out to infinity. What is my range? My smallest possible output is 0, and if we travel vertically, you'll notice it's slow, but it does keep going higher and higher and higher and closer to infinity, just slowly. So I'm just getting back to the view where we started. And recall, we always reflect these about what line when we draw our inverse functions. If you said y equals x, you're correct. So go ahead and graph y equals x. Then there's this great tool right here reflect about a line. You can actually reflect about a lot of different things. So let's just reflect this about the line. So I'm going to click on my original function, then the line y equals x. And you notice it automatically sketched out what the inverse looks like. This here is my original g of x, and this is my inverse function along the domain. If you notice the domain of my inverse function, I can put in a number as small as 0, and I can put in numbers as large as infinity. So my x values keep getting larger and larger. I know it is difficult to see, but it will keep going off to infinity forever and ever. Actually, a better way to see this is if I squish this down, you notice that my x values keep getting larger. All right, so what is the range of this inverse function? My smallest input starts here at 5, and that's a little hard to see. So there it is. There's that smallest input of 5. So what is the range of this inverse function? My smallest input is 0, and if I evaluate at 0, I get 5. And I can see that this is 5. If I adjust my graph of it, that's exactly 5. And then how large do my outputs get? Again, you notice I just keep going up higher and higher to infinity. So we have certainly verified. The domain of g of x starts at 5 and goes to infinity. The range of g of x starts at 0 to infinity, and we just swap the two to get the domain and range of our inverse function. With that, let's wrap up the lecture of section 3.8 with an application problem involving inverse functions. Example 5, solving an application with a cubic function. So a mound of gravel is in the shape of a cone with a height equal to twice its radius. The volume of the cone in terms of its radius is given by v equals 2/3 pi r cubed. Let's find the inverse of v. So I want to solve this. Now let's stop and think what the inverse of v will give us. Right now, we put in a radius and we get out a volume. To get this inverse, we're going to put in a volume and get out a radius. So I'm not going to swap these variables around. I'm just going to go ahead and solve this for r. So let's multiply both sides by the reciprocal of 2/3, which is 3/2. 2/3 times 3/2 is just 1. So on this side here, on the right side, I'll end up with pi r cubed. And on the left-hand side, I'll end up with 3 times v divided by 2. Let's keep going. I need to divide both sides by pi now to get 3v over 2 pi equals r cubed. And again, I divided this side by pi, which is equivalent to multiplying by 1 over pi. Finally, take the cube root of both sides. You'll end up with 3v over 2 pi inside the cube root equals r. So now we pop a volume into this function and we get out a radius. What is a meaningful domain for this original function? Now let's consider our inputs. Our inputs are r's, and these r's are a radius. What is the smallest possible radius you could have? Well, 0. If you have a radius of 0, this means you have no cone of gravel because your radius is 0, so you have no gravel. But we could keep getting larger and larger to infinity. Now, realistically, no one is going to have a cone of gravel with an infinite radius. We could have a radius of 10 feet, of a mile, if you getting that big, it'd be a pretty large cone. with a pretty large volume, but realistically, somewhere between 0 and infinity lie the only possible inputs for this original function. With that, let's look at part C. Use the inverse function to calculate the radius of such a mound of gravel measuring 100 cubic feet. So this is the volume. Let's use the inverse function we found in part A, that's up here. So I have r equals the cube root of 3v over 2 pi is the cube root of 3 times 100 over 2 pi. Using your calculator, you should get that this is approximately 3.63. Now, what are my units? My original units are cubic feet, that is feet cubed. And if I take the cube root of this, I should just end up with feet. So this mound of gravel has a radius of 3 feet. This concludes our lecture for section 3.8.